এই সুদীপ,
স্টার্ট
স্নেহাশিস
স্যার।
সুপ্রসাদ কোনো
স্টার্ট স্যার।
কোয়েশ্চেন আছে কি? হ্যাঁ, ঠিক আছে।
হ্যাঁ, না মানে ঠিক আছে।
স্যার স্টার্ট স্যার।
ওকে, ফাইন। Hello and welcome to the first live session of NPTEL course Thermal Physics. Mm, so you can post your questions in the comment of the YouTube link and we'll be trying to answer this. Okay, so before the question starts coming in, let me try to answer one question that has been asked in the forum. Okay, so let me first do this. Yeah. So the question was whether um, whether the ideal gas law can be proved from theoretical point of view, pure theoretical point of view. Okay. So first we start with this question. So basically we have to prove the ideal gas law PV equal to, so we can write either N kBT or we can write that as mu R T, where mu is the number of moles. Okay, so now if we recall, according to the kinetic theory, the pressure expression P is equal to 1/3 m n c RMS square. So we take this expression and we just substitute for this CRMS. What is CRMS? CRMS is 3 kBT by small m. So we just substitute 3 RMS, CRMS square is equal to 3 kBT by small m. 3 cancels out, m cancels out, which leaves us with n kBT. Now what is this n? N is nothing but capital N by V, that is the number density over here. So remember the small n. So that is why we start writing mu, the mole fraction as mu, because it might not, we should not confuse between this n and the mole fraction or the number of moles rather. So we write the number of moles with mu and n as capital N by V. So this is simply N kBT. Now, if we rearrange this relation, P is equal to N by V kBT, we get PV is equal to capital N kBT, which is, so just by rearranging this, we get this one, which is just the ideal gas law. So that means starting from elementary kinetic theory without, or rather within the framework of elementary kinetic theory, under the assumption that all molecules are perfect sphere, they are having elastic collision and their point particle, there is no other interaction apart from the collision, we can prove that ideal gas law. Okay, so let us see if there is any question in the forum. Do I check for comments? Okay, so far I don't see any comment over here. Okay. Yes, so Shomprasad and Snehashis, is there any other question uh, in the forum, NPTEL forum that needs to be discussed here? Please, you can also write that in the YouTube comment link. Is there any other question that needs to be discussed in the in the forum that has remained unanswered? Let me see. Or degree of freedom related. What is that? Any specific question? Any specific question about degree of freedom? Linear triatomic. Fantastic. Okay. So let's try this. Okay. First of all, let us start with linear diatomic molecule. Let's say we have a molecule which can be modeled by this. We have two masses, and this is connected by some bond. Um, if the molecule is rigid, in case the molecule is rigid, then how many number of DOFs present? 5 degrees of freedom. Out of that 5, 3 translational plus 2 rotational degree of freedom. 3 translational means basically translation in all these 3 directions, x, y, and z. So let's call it x, y, and z. And 2 rotational because we can have rotation around z-axis or around y-axis, but no rotation is allowed around x-axis because we generally considered, when we consider a molecule, we consider these as point masses. So a point mass, so this molecule is a point molecule, uh, or rather 2 point masses connected by a massless rod. We can model it like this. So that is why no rotation is allowed around x-axis. So 2 rotation. Now, if we call it non-rigid, so this is for the rigid one. Now, if we call it non-rigid, then we can actually have 7 degree of freedom. Because once we consider the vibration, it starts to vibrate. Just a minute. Yeah. So the molecule starts to vibrate in this fashion, this manner. So it can go, these 2 atoms can go out together or they can come in together. So this is the pattern of vibration we have. So we have 7 degrees of freedom because there will be 3 translational, 2 rotational as before, and there will be 2 additional vibration degree of freedom. Why 2? Because please remember the definition of the thermodynamic definition of degree of freedom is number of independent coordinates, sorry, not number of independent coordinates, but the number of quadratic term in the energy expression. Okay, I'll just mark the direction of vibration once again. So it could either go out together or come in together. Now, this type of vibration, it can be put into perspective by when we draw a one-dimensional spring mass system with a spring constant K and a mass M. Okay. So this rod is not a rigid massless rod anymore. It's a rigid, or sorry, it's a massless spring with a spring constant K, and this individual masses, this mass cap, this mass M is a effective mass of this two-body system. Now, in this case, the total energy E can be effectively written as half K x square, where x being the displacement from the equilibrium position, half kx square plus half m x dot square, x dot being the velocity. So that means this is one quadratic term and this is one quadratic term, which corresponds to 2 degrees of freedom. So basically, a two spring or two diatomic molecule, two atom connected by one vibrating bond, can be represented by a single spring mass system, which corresponds to 2 degrees of freedom, vibrational degree of freedom. Okay. Now, and as per equipartition theory, each vibrational or each degree of freedom uh, gives you an energy of half kT. Per degree of freedom per molecule, you get half kT. So for a rigid diatomic molecule, the energy of a rigid molecule is 5 half kBT, whereas energy corresponding to a non-rigid molecule is 7 half kBT. So this is the total energy. We can write this as E also if you like. So better to write it as E. Okay. So this is the diatomic molecule. What happens in the triatomic molecule case? In triatomic molecule, once again, we just first draw this molecule. Here we have one mass, then another bond,
Screen is not
another
visible.
mass. Yes.
So writing screen is not visible.
Yes.
Oh, should have said that. You should have said that earlier, no?
I have seen all
I
now.
am not checking this one. I should have said that a little louder. Anyway, now is it visible?
Yes,
I explained it all throughout, and now you are saying, okay. So this is a diatomic molecule. We have 5 degrees of freedom. Out of the 3 rotation, 2 translation, and non-rigid molecule, 3 rotation, 3 translation, 2 rotation, and 2 vibration. And this is your equivalent picture, spring mass picture, K and M. So it is half k x square and half m x dot square. So this is 3 half kBT, the energy for a rigid case, and for non-rigid case, it is 7 half kBT. Now for the triatomic molecule, once again, we have, is it all visible now in the screen?
yes, sir.
Yes.
Oh, okay. So now how many, once again, we considered the rigid case. In here, we will have once again 5 degrees of freedom. So, sorry, should have written that. It will be 5 because there are 3 translation plus 2 rotation. Correct. Rigid means. So basically for rigid molecule, the diatomic and triatomic molecule has not much of a difference because it can only rotate in 3 directions. This is my x, y, and z. Sorry, it can translate in 3 directions and it can rotate in only 2 directions. So if if this is x, this is y, and this is z. So it can have translation in all 3 directions. If it is rotation, then x rotation will not be considered because it's a one-dimensional molecule, and y and z rotation will be considered. So it will be 3 plus 2. Next is non-rigid. Okay. Here my DOF will be 5 plus 2 plus 2. Why? Out of this 5, once again, 3 translation plus 2 rotation. This 2 is symmetric stretching. This 2 is asymmetric stretching, vibration. Both are vibration. What is symmetric stretching and what is asymmetric stretching? If you have taken a course on classical mechanics, or if you have read any standard textbook in classical mechanics, uh, you should be familiar with this. There is also an NPTEL video, my NPTEL video, old ones on classical mechanics. There also, if you look at the small oscillation chapter, this has been worked out in details. So basically, there could be two different types of vibration. Linear vibration. Please remember, we are talking about linear motion. Here, bending is not allowed. Bending means uh, the movement of this molecule and this molecule perpendicular to the direction of this bond. But it is vibration is possible only along the direction of this bond. So we can have a symmetric stretching and an asymmetric stretching. What is a symmetric stretching? Symmetric stretching is when these three molecules, out of these three molecules, the central molecule remains stationary, and the outer molecules, they move, sorry, so they move out together and comes in together. So let's say out of three molecules, the middle one is stationary. We don't consider the movement of that, and the other two, it moves out and comes in together. So in that case, this will be equivalent of having one particular type of vibration. So it can be basically represented by one single normal. Okay, I am not going into the details of what normal mode is, but normal mode, you can consider that to be the independent coordinate corresponding to any type of motion. I mean, there could be normal mode for translation and rotational motion as well. And there will be one normal mode corresponding to this vibration. Now, if we call this normal mode as Q symmetric, then the equivalent energy for this symmetric mode can be written as half M effective Q symmetric dot square plus half K effective QS square. So once again, there's two quadratic term. So that is why it will be considered as 2 degrees of freedom for the symmetric stretching. Okay, so I'll just write SS here. What I have written here is actually stands for symmetric stretching. And AS stands for asymmetric stretching. Okay, fine. So this is for the symmetric stretching. Now for what happens for asymmetric stretching? Asymmetric stretching, in case of asymmetric stretching, the central molecule does not stay stationary. It can move in a direction opposite to the outer molecule. For example, if this molecule is moving in this direction, then the outer molecules will move in this opposite direction. And in the reverse cycle, when the central molecule will be moving in this direction, the outer molecules will be moving in this direction, opposite direction. So what is the advantage of this? The advantage of this is, or what is the reason of this movement? The reason being the center of mass should not change. In a pure vibration, the center of mass should not change. Okay, so this is called the asymmetric stretching, which is written here. So this is asymmetric stretching, and the previous one was symmetric stretching. Here also we can define a degree of or normal mode as QA, and we can write the energy of the asymmetric stretching as half M. Okay, we should not use the same symbol for 1. So we just call it 1 and 2 M effective QA square plus half. So here also we put 1 half K effective 2 Q. Sorry, this is QS dot square and this is Q square. So once again, two quadratic terms. Now, what are the actual form of M effective 1, K effective 1, M effective 2, Q effective 2? This can be worked out. Not very complicated. It can be done, but that is not important. Important point is that we have two quadratic terms corresponding to asymmetric stretching, which gives rise to 2 degrees of freedom, and similarly two quadratic terms for the symmetric stretching, which gives rise to the symmetric vibration. So basically it gives rise to 2 degrees of freedom. So altogether 5 plus 2 plus 2, 9 degrees. So for rigid diatomic molecule, triatomic molecule, the degree of freedom remains 5. Whereas for non-rigid triatomic linear molecule, please remember, as long as there is only stretching vibration, the molecule can be considered linear. If the molecule starts bending, then it cannot be considered linear anymore. And then the number of degrees of freedom will be adding up. We are not considering that at present. We are just considering the linear triatomic molecule uh, vibration. So we have 5 plus 2 plus 2, total 9 degrees of freedom. So the energy correspondingly will be 9.5 kBT. Okay, so this is the discussion on degree of freedom. Now let us see if there is any comment. Okay, there are a few comments. Let me see. Ask about the dependence of temperature in the different transport phenomena. What was not, why was not the temperature? Which one only half power? Okay. Um, so there is a doubt in assignment when the answer was given wrong. There was some confusion in rigid and non-rigid there. It should have been D. But okay, I think assignment 1, question 9. I think this is the question about diatomic molecules, right?
Yeah, it was about that,
Diatomic
the
molecules,
mixture.
right?
Yes. So,
And I think we have to, there was a mistake definitely, and we have to, you know, reevaluate the assignment because taking that one particular problem out, right? So have you communicated that with the NPTEL team?
no, not yet, because
Not
there
yet.
was some
Okay.
other.
So yes, there was a problem regarding this one, the last problem. Sorry, the problem number 9 of the assignment 1. And yes, so we have to basically consider, we will take that out of the evaluation. Okay, fine. Next is, there is a question. Rahul, you want to ask anything? You can ask. See, there was a question regarding temperature component of mean free path considered when taking the dependence on temperature. I don't understand. Only, what is the question? Only half power of T was considered for thermal conductivity and viscosity, while 3/2 power considered for diffusion D. Okay, let me quickly go to the respective class notes. Only then we'll have an idea. Mm, Which week was it? Can anybody tell me? Should be around 11. Well, transport should be around 11. Right. Okay. Let's see. Mm, Lambda. Okay. I'm just trying to find out the relevant notes, relevant portion, section of the note. So that, right. Okay. So I think I have got the question now. I think I have got the question now. Well, just give me a few minutes before I can answer.
Probably it was on lecture 13.
Lecture 13, exactly. Looking at that now. Lecture 13, lambda c bar. Right. Diffusion constant. Diffusion content should be in lecture 14. No, or 15. Diffusion constant is 3 half. Okay, lambda c bar. So here 7, 13, 12. Huh, right. This is this. Then thermal conductivity will be in lecture 13 again. So as diffusion constant. Yeah. Okay. So the question is, once again, I'll just read the question. Mhm. Yeah. The question is, why was not the temperature corresponding to mean free path component of mean free path considered when taking the dependence on temperature? Only half power of T was considered for thermal conductivity and viscosity, while 3/2 power considered for diffusion D. Okay. So if we go back here, okay, open a new page. What is the expression for mean free path lambda? Lambda is equal to, once again, lecture 7. If we go back to lecture 7, okay. Not sorry, sorry, not lecture 7. Go back to lecture 6 actually. Warden. Just give me a second. I'm just trying to. I thought I found it. I lost the lecture 12. Where is it? Yes, lecture 12. Right. Yes, yes, yes. Got it. Got it. Lecture 12. Now, if you remember, okay, if you let us start from lecture 6. Okay. So, lecture 6 is, if you go to lecture 6, then the last expression that we have derived is lambda is equal to C bar divided by N sigma C. C was in red. So, lambda is C
Writing pad
bar.
is not visible.
Sorry. Oh, not
Writing
visible.
screen.
Okay, okay,
Yes.
okay. Sorry. Screen share. Right. Now is that visible?
Yes, it is.
Lambda sigma and lambda sigma c trend. And then if you remember, we wrote it like this, C. Now, what was that C? That C was taken from the first order correction of Clausius. Huh? Sorry, the first order correction of Clausius, C bar was considered to be root 2. Sorry, not the first order, second order correction actually. Second order correction was this C is equal to root 2. Sorry. Yes, is equal to root 2 C bar. So if we substitute that, and we have used this value, so if we substitute that, then we have C bar n sigma times root 2 C bar. This C bar cancels, and finally we get root 2 n sigma. Now, sigma is nothing but the molecular cross section, which is, I think, 4 times the effective. So the expression for sigma is 4 pi d square. Was it 4 pi d square or simply pi d square? Just a minute. 4/3, right? So sigma will be determination of C and
It is pi d square, I guess.
pi d square, simply no 4. Right? There will be no 4 over here. So it will be simply pi d square. Okay. So this pi d square, it's a purely what you call the molecular property, and it does not change with temperature. Same as n. If you consider a closed this one close an enclosure which is totally closed from all sides, you can boost the temperature of that, but will n change with temperature? No. So the dependence of lambda on temperature is a zeroth order dependence. So that means there is no dependence actually, because sigma does not change. So basically it is pi d square, and n also does not change for a closed system. Of course, if you have an open system, if you increase the temperature, the density will decrease. In that case, lambda will vary. Uh, the mean free path of the assembly will vary with temperature. But otherwise, lambda has no direct dependence on temperature as per this particular theory. Okay. Now, let us look into the expression for eta. Eta is 1/3. What was this? Once again, we go to lecture number 12 and 13. This is lecture number 13 I am looking at. No, 13 is different. Right? Sorry, my things are coming on my screen actually. That's a problem. Yeah, lecture 12 is here. Okay. So eta is equal to 1/3 mn c bar lambda. Okay. So now let us write this. Eta is equal to 1/3 mn c bar lambda. Mn is equal to rho. So 1/3 rho c bar lambda. Lambda has no dependence on temperature for a closed system. Rho has no dependence on temperature for a closed system. But for the very simple reason that same way I said that n does not change for a closed system as a function of temperature, your lambda also does not, or sorry, your rho also does not change as a function of temperature. So the only temperature dependence comes through this C bar. And this C bar has a temperature dependence. What is the expression for C bar? C bar is equal to 8 pi kBt by 8 kBt by pi m. Sorry, 8 kBt, not pi will not be here, but here 8 kBt by pi m. Everything is constant except t. So it will be a root t dependence. C bar means a root t dependence. Same goes for k. What is the expression for k? Once again, I'll just have to look at the lecture notes. I don't remember those offhand. Yeah, So for that, K is equal to 1/3 lambda C bar CV and CV V, hmm, or rather CV V, and that's it, right? CVV is the N heat capacity per unit volume. We can also convert it to heat capacity per unit mole, and we can write 1/3 lambda C bar, lambda C bar, rho by small m, rho by capital M, C V, where the CV is the molar heat capacity per unit volume. Rho M is the molar mass, which is, again, these are not temperature dependent quantity. At least for the time being, we don't consider the temperature dependence of CV, which comes at a much later time. So if we go by elementary theory, once again, lambda has no temperature dependence. Rho has no temperature dependence. M has no temperature dependence. CV has no temperature dependence. So only temperature dependence once again comes from root C. So C bar, and that is why we have a root T dependence. But now if I look at the expression for the diffusion constant, what is the expression for diffusion constant? Diffusion constant expression will be in lecture 14, which is 1/3 C bar by lambda. Okay, wait. Oh, I think there is a mistake over here. I understand. I think there is a mistake. T is equal to 1 by T. Okay, I got it. So the expression is once again D is equal to 1/3 C bar lambda. And here there is some logic by which I am saying D is equal to proportional to 10 to the power 3 half. Okay. Mm, okay, I got it. So as per the notes in lecture 14, so I just wrote that lambda is varies as T, but I have not considered the same variation for previous notes, lecture 12 or 13. But in lecture 14, I wrote lambda proportional to T, and then I wrote D is proportional to T to the power 3 half. So that's where the question comes. Okay, so I'll check that. I think there must be a mistake, or there must be a misunderstanding somewhere. Okay, so I'll check that and I'll get back to you. Thank you for pointing it out. There is some discrepancy between the notes. I can see that. Okay. Let's see if there is any other question. Yes, there are questions. Yes, that's where my doubt came, right? Okay. I think this is where the problem is. Okay, I'll check that and I'll get back to you. Any other questions? Okay, so no more question is coming in the forum. Okay, Snehashish and from Prashad,
Yes.
can we discuss anything else?
Someone asked about gamma function. So in kinetic theory of gases.
Oh,
So
did I miss
if
that?
that can be, yes.
Gamma function, what
Yeah,
is to
that
be
is,
discussed?
yeah. So,
Where is who gave this question?
so someone
Somebody.
asked it in the forum.
Forum
Let
or
me,
now in the YouTube?
uh, in the forum.
In the forum. See, gamma function is something that frankly I also don't understand. So I cannot I am not the right person. It's a mathematical function. Certain standard integration can be written in terms of gamma function, and there is a formula given, just like we have Legendre polynomials and like for example other polynomial functions. We can also have what you call a gamma function integration. If a particular form has come for the gamma for that integration, we can represent that as a gamma function, and gamma function has uh, a particular value. So that's all I know. What are the mathematical basis for gamma function, and is there a way of, generally typically this type of functions, they come from solution of some particular type of differential equation, like Legendre polynomial, Legendre polynomial, Bessel function. All these are, or Hermite polynomial. All these are solutions of certain types of differential equation. So whether gamma function is also from a solution of a type of differential equation, I don't know. So I cannot really answer. Okay. Anything else? Any other question? Okay, if there is no other question, I think it is time to close this live session. It's already 45 minutes. What should we do? NPTEL team, do you have any question?
No, sir.
Okay. I mean, fine then. So can we close this session now?
Okay, sir.
Okay. So I think there is no other question coming in YouTube channel also. So I think it's better to close it. One doubt which we'll be looking at. Sure. Okay. I'll answer. Okay. Then let's log out. Thank you everyone for joining, and hope to see you in the next live session.